this video, I would like to talk about the observer, which is a very important and one of my favorite topics in this course. Okay, what's the observer? So in the previous lecture, we designed a state feedback controller. We learned how to design that. Okay, we have a state space structure like this. Okay, h times u of k and y of k is, of course, it's equal to c times x of k plus d times u of k. The major problem with the state feedback controller is we assume that we have direct access to all of the states of the system. But in actual systems, we generally measure y, which is the output, and x are like intermediate variables. In most of the cases, we don't have direct access to all of the states of the system. It's possible that we can access to some of the states, but not all of them. So what's the idea in observers or estimators or filters? There are different kind of names throughout for these kind of systems, but the basic idea is similar. Okay, first of all, we know G, we know H, we know C, we know D, and moreover, we know U, because U is the input of the system. Okay, we don't know X, we measure Y, so we know also Y. And the critical point is Y, which is the output. Okay, so what we do is, we construct a simulated system which actually runs in real time, parallel to the actual system on our embedded platforms. And simulated system looks like this. X hat of k plus 1 is equal to g times x hat of k plus h times u of k. Okay, since we know u is real, h and g is known, but x hat is different from the actual system because we don't know x. So x are our predictions, our assumptions. Y hat of k is equal to c times x hat of k plus d times u of k. That's it. Okay. So what I can do is, I can run the simulation in parallel to the actual system, but the problem is if I don't have any connection, if I have an error in X, it will preserve throughout the simulation, right? So I need to technically match these two systems, possibly connect them such that this X hat somehow converge to the actual X of the system over time and possibly as fast as possible. This is a requirement from an observer. So what I do is, the basic idea, very simple. I try to compare y of k and y hat of k. So actual output and predicted output. One is measurement, one is estimation. And this difference is key for constructing an observer. So what I do is, I somehow obtain this difference. Okay, so it is like difference between reference and output signal, but this is difference between output and predicted output, and I feed to my original system through a slightly non-intuitive structure, and I add a new term L. Okay, so L is a parameter times, okay, so this is to take y of k minus y hat of k. So let's look at this in a second. So when output of the actual system is equal to the output of the prediction, this term is equal to 0, so it doesn't affect our simulation. It shouldn't affect our simulation, and it means that it's kind of everything is normal. Just simulate the system normally. But when there is a discrepancy between output and predicted output, then we need to modify our observer such that it will technically approach the original system, especially from the perspective of estimated states. Okay, good. So let's try to analyze this. And in order to do that, I will define a new variable, a e of k. It's an error, but now this error is between xk and x hat of k. Okay, so when I connect two systems using this feedback, it's actually a feedback structure, it becomes connected and it becomes a combined state space of the system. Okay, so state space is composed of x and x hat. We have like 2 times n number of states in our system. So what I can do is I can change variables. Of course, I can always do that because we have like infinite many different state space representation for the same system. Okay, and this will really help us. Okay, this is our new state, and I can compute x e to the power k plus 1, which is equal to x k plus 1 minus x hat k plus 1. What is x k plus 1? It is very simple. G times x of k plus h times u of k minus g times x hat of k minus h times u of k minus l. Okay, so what is y? I don't need to use y now because it's the state update equation from the perspective of error. What is y? Y is equal to c times x. What is y hat? C times x hat. So instead, what I can do is this: L times c times error of k. Right? Okay, that's good. So let's analyze the other terms. H times uk, h times uk. There's a okay. So this is plus. This is minus here. So they will cancel out each other. G times x minus g times x hat. So this is equal to g times error of k minus LC error of k. I think that's perfect for us. This is equal to g times LC error of k. It's equal to error k plus 1. Okay, we have an equation, an isolated equation from the perspective of error dynamics. There is no input. Okay, so this is an autonomous system, and it's only driven by a state update matrix. Okay, so what we want from the error? Error is the discrepancy between x and x hat. We want this to be small, as fast as possible, 0 as fast as possible. Of course, at the beginning of the simulation, when there's an error or perturbation coming to the system, there will be errors. And we want to cancel this error as fast as possible, and we can do it by designing the eigenvalues of the G hat matrix, right? And as you can see, this is very similar to the state feedback controller design. We obtain a new G hat, which technically comes from the state feedback rule, but now we have an observer rule, which is technically producing a G hat, and we want this G hat to be as fast as possible, and we want eigenvalues such that initial condition will go to 0 as fast as possible. So we will use an observable pole placement technique to design L. So G is equal to G hat, G minus LC, okay? And what we do is we start with a set of desired eigenvalues, okay, such as like lambda 1 star, it goes to lambda n star, and we come up with an ideal P star of Z, which is equal to Z minus lambda 1 star goes to Z minus lambda n star. Okay, then what we do is we compute determinant Zi minus G hat. We equate it to B star of Z. And if you do that, you will obtain some set of equations. Then you will solve it to obtain your observed parameters. Let's do it in a simple example. Okay. Rg is equal to 1, 0, 0, 2. Rc is equal to what? That's okay, so 1 minus 1. And L is an element of Rn. Let's call it L is equal to L2, L1. Okay, so it can be L1, L2, L2, L1, it doesn't matter. In this video, in this lecture for now, I will only teach you the direct design method, so ordering of the L1, L2 is not critical. There's a different design technique which is called using observable canonic form, which is okay, but for like in the midterms, it's not practical. It's important for different kind of analysis where you have high number of states in the system. Okay, good. So just keep in mind that the idea is computing determinant Zi minus G hat, okay, which is pretty easy. This is equal to determinant, okay, Z minus 1 plus L2 minus L2, L1, Z minus 2 minus L1. You can check my computations. They should be correct. If I computed that, my actual characteristic equation is this. L2 minus L1 minus 3 plus L1 minus 2, L2 plus 2. Okay, so what do you want? Okay, so in this problem, I want my lambda 1 and 2 to be equal to 0. So I want a deadbeat observer. So what is a deadbeat observer? We know that deadbeat controller and deadbeat observer is similar. And it's even more like practical because we are only simulating the system. So technically the magnitude of L is not very critical. Okay, so deadbeat observer estimates the actual states of the system in finite time. So the error between X and X hat will go to 0 in only 2 steps because this is a second order system. So it's a really nice thing to obtain because if I approach to 0 in terms of the error between actual and real states as fast as possible, it means that maybe I can use this as a controller very nicely or effectively if I apply a state feedback rule. And this is the basic idea, and I will talk about this later. Okay, so under this requirement, my desired polynomial will become z squared plus 0 plus 0, which means that I want to equate both coefficients to 0. And as you can see, both L1 and L2 comes in a linear term. It's one of the most powerful and beautiful parts of state feedback and linear observer design, because my parameters in these characteristic equations comes in linear terms, which I need to solve very quickly. And I will find that L2 is equal to -1, L1 is equal to -4, so L is equal to -1, -4. Okay, and this is my observer. And if you check the eigenvalues of the G hat, you will see that they will be both equal to 0, which means that I will reject all of the initial error between actual state and real state in finite time.